Welcome to the Physics Trek channel, where you can partake of a spoonful of incremental success. This medicine is free of charge and might just do you some good. I'm Alan J, here with another prickly worked solution that will hopefully keep your attention and get those underused brain cells stirring into action. In this video, like in all the ones before, you'll learn best practice in setting out and solving problems. But before we dive in and get our hands dirty in equations and numbers, I thought we might pause a short while and consider some of the language we use. As you've probably gathered by now, none of this work deals with curves. It's simply motion in a straight line. And you guessed it, there is a word for this, and the word is rectilinear. We are talking about rectilinear motion. Now in reality, this type of motion rarely exists. A bullet fired horizontally might keep this motion for a very short time, but then it will follow a slow curve called a parabola. So look out for this word, rectilinear. It will crop up again in wave propagation, lenses and mirrors, and in a host of other places. And now let's get back to our question. Question 6. This is in two parts and bears some resemblance to question 4. You might have heard this story before. A stone is thrown vertically upwards from the top of a cliff. Well, in this little gem, you have to work out how high the stone goes and the height of the cliff top above the sea. Here it is. Question 6. A stone is thrown vertically upwards from a cliff top with a velocity of 40 meters per second. Part 1. If after 4 seconds the stone reaches maximum height, how far is it above the cliff top? Part 2. If the stone strikes the sea after 10 seconds, what is the height of the cliff top above the sea? Down the left side of the screen are the two sets of reference equations, one for upward movement and the other for downward. The first piece of advice is to thoroughly understand the question before doing anything. That's true of any question. And to help you with your understanding, you need to lay out all the knowns and unknowns in a clearly labelled diagram. Because we have two separate movements of the stone, one up and the other down, the use of subscripts to name quantities is particularly important. So here is our cliff, dotted lines for the sea level below, the line of the top of the cliff and the maximum height reached by the stone. We label the height of the cliff D, and the upward initial velocity of projection U1. The final velocity at maximum height we'll call V1, and the height of the stone above the cliff, call it S1. The time to reach maximum height will be T1. Looking at the downward movement, initial velocity of the falling stone is U2. Notice this is the same as V1 in the first part of the motion. When the stone hits the sea, it does so with a velocity V2. The distance fallen is S2, the time for the fall is T2, and of course the stone accelerates downwards at g meters per second per second. Let's write all that out with some numbers in it to let it all sink in. U1 equals 40 meters per second, V1 equals 0 meters per second, T1 is 4 seconds, and we are asked to work out S1. U2, as we said before, is 0 meters per second. D, the height of the cliff, we need to find. Now if T2 is the time for the rock to fall, then T1 plus T2 equals the total time, which is 10 seconds. Also, S2 equals S1 plus D. The height of the cliff D plus S1, the maximum height of the stone above the cliff, equals S2, the total distance the rock falls. Now to the first part of the calculation. The question asks for S1, the stone's maximum height above the cliff top. Well, the stone is moving upwards, so we choose from the top equation set. We have U1, V1 and G, so U squared minus V squared equals 2GS is the obvious choice. Writing this out with the subscripts, U1 squared minus V1 squared equals 2GS1. We need to make S1 the subject of the equation on the left, so turning the equation around we have 2GS1 equals U1 squared minus V1 squared. Dividing both sides by 2g to leave S1 on its own, we have S1 equals U1 squared minus V1 squared divided by 2g. Putting the numbers in, S1 equals 40 squared minus 0 squared divided by 2 times 9.8, which equals 81.633 meters. S1, the maximum height of the stone above the cliff, is 81.633 meters. The second part of the question asks for the height of the cliff top above the sea. In other words, we need to find D. Before we do this, let's have a closer look at the times and distances involved. T1 is the time for the stone to reach maximum height from the top of the cliff, while T2 is the time for the stone to fall from maximum height to sea level. We are told that the total time the stone is in the air is 10 seconds, so looking at the diagram, it is clear that T1 plus T2 equals 10. Now to the vertical distances travelled. D is the height of the cliff above the sea, S1 is the maximum height attained by the stone above the cliff, and S2 is the distance the stone falls from its highest point to the surface of the sea. So S2 equals S1 plus D. Remember, we need to find D. We worked out S1 in the first part of the question. Now to work out D from the equation, we need to find S2. To do this, we need the time interval T2. We know that T2 plus T1 equals 10. T1 is 4, so 4 plus T2 equals 10. T2 equals 10 minus 4, which equals 6. T2 equals 6 seconds. Now to work out S2, we need an equation from our motion downwards list. The obvious one with our subscripts added is S2 equals U2 T2 plus a half GT squared. Putting the numbers in and remembering that U2 is 0, S2 equals 0 plus 0.5 times 9.8 times 6 squared, which comes to 176.40 meters. Going back to our equation for S2 in terms of S1 and D, S2 equals S1 plus D. Changing the equation around and taking S1 to the other side and changing its sign, we have D equals S2 minus S1. Putting the numbers in, D equals 176.40 minus 81.633, which equals 94.767 meters. So here is our answer summary. Answer to part 1 of the question: maximum height of the stone above the cliff is 81.63 meters, and to part 2, the height of the cliff above the sea is 94.77 meters, with both answers rounded to 2 decimal places. Well, our revels now are over, for the time being anyway. Alas, question 6 is the last in the Acceleration Due to Gravity series, but I'm sure other questions will be added over time, so if you find some that are cunningly devious or give you grief, please do drop me a line. I hope all these videos have helped you in some small way and that you enjoyed watching them. I certainly enjoyed making them. Remember, enjoyment is the key to your success too. Always embrace new things. Don't see them as impossible walls to climb. See them as new opportunities to learn and challenges to overcome. So if you really did like the video, I'd appreciate you giving the channel a like, a favourite or a subscribe. Remember, most of the unanswered intermediate mechanics questions are on the Physics Trek website now. So go on, have a go at them and stay ahead of the game. A work in progress is to give answers in brackets at the end of each question. Check it out. Anyway, do look out for the next work solution. The following topic is the conservation of momentum, so look out for the release of the first question in the series. And if you want to recap on the previous video, question 5, just click the link. Remember, comments on the show, suggestions on how to make it better, or ideas for new videos are always welcome. Thank you all for watching.